This video explains the structure and operating principle of a planetary gearbox in more detail. Let us first look at a so-called stationary gearbox, which is characterized by the fact that the gears have stationary axes of rotation. The animation shows a yellow drive gear that first drives a blue idler gear. This in turn sets the red output gear in motion. In principle, this is a two-stage gearbox. The yellow drive gear and the blue intermediate gear form the first gear stage. The gear ratio of this gear stage results as indicated from the ratio of the number of teeth of the two gears. The second gear stage is formed by the blue idler gear and the red output gear. The gear ratio of this gear stage also results as indicated from the ratio of the number of teeth of the two gears. The total transmission ratio of this two-stage stationary gearbox, therefore also called stationary transmission ratio, is calculated by multiplying the individual gear ratios I1 and I2. It can now be seen that only the number of teeth of the output gear and the input gear are relevant for the overall transmission ratio. The number of teeth of the idler gear has no influence on this. This fact will become important later on. In principle, an internal gear can be used instead of the external gear. As long as the ring gear has the same number of teeth as the external spur gear, the overall transmission ratio will not change. Only the direction of rotation of the output gear is reversed. Usually, the rotational axes of the input and output shafts are not aligned, but are offset. However, by properly selecting the diameter and therefore the number of teeth of the idler gear, it is possible to ensure that the input shaft of the yellow gear and the output shaft of the red ring gear are aligned on a common axis of rotation. At this point, we use the previously explained fact that the number of teeth of the idler gear has no influence on the overall transmission ratio anyway, and can therefore be chosen as desired. If the input and output shafts are to be coaxial on a common axis of rotation, the pitch diameter of the intermediate gear must be equal to the difference between the pitch circle radii of the output and input gear. Since the number of teeth is directly proportional to the pitch diameter, the number of teeth can be used instead of the pitch diameter. Therefore, the number of teeth of the idler gear must be half the difference between the number of teeth of the ring gear and that of the input gear. In this case, the red ring gear has 48 teeth and the yellow drive gear has 12 teeth. This results in a number of 18 teeth for the intermediate gear so that the axes of rotation of the ring gear and drive gear are aligned. A disadvantage of this gearbox is that the output shaft and the input shaft are subjected to bending due to the one-sided flank force of the idler gear. In the animation, F is the force of the idler gear acting on the flank of the ring gear. However, bending stress can be avoided if several intermediate gears are arranged symmetrically so that the flank forces compensate each other in their bending effect. In the case of three idler gears, the drive and output shafts are no longer subjected to bending, but only to torsion. At the same time, the circumferential force generated by the torque of the drive shaft is distributed over a total of 3 gears, reducing the flank forces of each gear. This significantly increases the maximum torque that can be transmitted. In principle, this gearbox is already the preliminary stage of a planetary gearbox. In the final stage, the idler gears are mounted on a so-called carrier. The carrier, in turn, is connected to a shaft and is guided coaxially through the output shaft, which is designed as a hollow shaft. The planetary gearbox is now complete in principle. In this operating state, it has the transmission ratio already derived. The mode of operation does not yet differ from that of the stationary gearbox described at the beginning. However, this changes when the planetary gear is used in a different way. The output does not always have to be on the ring gear. It is now possible to use the carrier as the output while the ring gear is firmly locked. In this case, the input gear drives the idler gears around the fixed ring gear. The idler gears rotate around the central input gear like the planets around the sun. Hence the name planetary gearbox. The transmission ratio of this planetary gear is now different to that of the stationary gear considered before. The gears previously referred to as idler gears are generally also known as planet gears. The externally toothed central gear is called the sun gear. The internally toothed ring gear is also referred to as annulus. Here too, the need for a symmetrical arrangement of the planet gears becomes apparent, as otherwise enormous unbalance forces would occur at high speeds. With a planetary gear, it is not only possible to lock the ring gear and have the output take place using the carrier. There are many other possible variants, which we will go into in more detail in a moment, and which each result in a different transmission ratio. This makes the planetary gearbox particularly suitable for shiftable transmissions, such as in hub gears of bicycles or in automatic transmissions of motor vehicles. The advantage of a planetary gear compared to a conventional stationary gearbox is the compact design and the advantage that all shafts are arranged coaxially. For very large transmission ratios, several planetary gearboxes can also be connected in series. Various transmission ratios can be realized with a planetary gear, depending on which shaft is used for the input or output. The various gear ratios are explained using the example of the planetary gear shown here with a sun gear with 12 teeth and a ring gear with 48 teeth. In this case, the largest transmission ratio of 5 is achieved if the sun gear is used as the input and the carrier as the output when the ring gear is locked. Interchanging the input and output results in the smallest possible transmission ratio of 0.2 as a reciprocal value. The direction of rotation of the input and output shafts remains the same in both cases. The second largest transmission ratio of 4 results in the present case if the sun gear is still used for the input, but this time the carrier is firmly locked and the ring gear is used for the output. The second lowest transmission ratio is again obtained by interchanging the input and output shafts and is then 0.25. However, the direction of rotation between the input and output shafts is different in both cases. Mathematically, the transmission ratio in such a case is also given as a negative value. A reverse gear can therefore be created with such a transmission ratio. Another way of using the planetary gearbox is to lock the sun gear and have the ring gear as the input and the carrier as the output. In this case, the transmission ratio is 1.25 while the direction of rotation is maintained. Interchanging the input and output results in a reciprocal transmission ratio of 0.8. With shiftable gearboxes in particular, it should not be forgotten that a so-called direct drive is also possible. In this case, all components of the planetary gearbox are firmly locked together. In this case, the transmission ratio is 1. Such a direct drive is used, for example, in 3-speed hub gears as the second gear. The various possible gear ratios are summarized in the table. The transmission ratios with the input and output reversed are shown in brackets. Negative signs indicate a reversal of the direction of rotation. The derivation of the formulas given for determining the transmission ratios is explained in detail in another video. However, it should be noted that the number of teeth of the planet gears has no influence on the transmission ratio for any configuration. The shifting of the various transmission ratios is carried out in shiftable gearboxes by so-called clutches, which enable the locking of individual components depending on the desired transmission ratio. For constructive reasons, not all transmission ratios listed in the table can be realized with a single planetary gearbox. However, by combining several individual planetary gear sets, the possible transmission ratios can be increased considerably. In practice, up to 3 planetary sets are common in a gearbox.